Okay, so our focus now is on product layouts, and recall that product layouts have a different objective than process layouts. Our objective here is going to be maximizing the utilization of each of the workstations. We're not going to worry so much about minimizing movement cost because the nature of the product layout itself is going to minimize the movement cost. So maximizing workstation utilization, whether we're worried primarily about the machines or the people or both, is more difficult than it might seem because of the discrete nature of the tasks that could be involved, and also because of the precedence constraints among the tasks. Consider this example down here. Suppose there's 3 tasks that need to be done to complete a product. Again, I got task A, task B, and task C, and it doesn't make any sense to break these tasks down into smaller elements. There's a certain amount of setup involved, and to try and break them down into smaller elements would simply expand the amount of time needed to complete the task, and that would be inefficient as well. Suppose further that I wanted a unit coming off the line every 2 minutes. Okay? And that seems possible because task B here takes 2 minutes and the other tasks take less time. Well, if because of precedence, and we're familiar with precedence from our discussion of project management, I can't do task B until I do task A, and I can't do task C until I do task B. So if I can only put 2 minutes of work at each workstation, okay, I got to start out with A, I got 1 minute of work going on at A, but I can't do B at that same workstation because that would bring me to a total of 3 minutes, okay, which is larger than the amount of time I want to have at each workstation. I want all units to move forward every 2 minutes because of the speed I want the line to go so I have sufficient output to satisfy demand. So in that situation, I have one task A at the first workstation. At the second workstation, I have task B, and then that leaves task C, which also only takes a minute, at the third workstation. So 3 workstations for the 3 tasks. It takes me a total of 4 minutes to do the work needed to make 1 unit, but for each unit that comes off the line, it's spending 2 minutes here, 2 minutes here, and 2 minutes here. The 2 minutes here are all work. Of the 2 minutes here, only 1 minute is work, and of the 2 minutes here, only 1 minute is work. So every unit off the line has spent 6 minutes on the line, but 2 of those 6 minutes have been wasted, basically, in idle time. A simple formula with a little notation enables us to quantify that percentage of idle time. So here's the same example I have with the 3 tasks in the 3 different workstations. Suppose there's 3 elemental tasks. Well, I've got 3 here. Well, and I'll call that, in general, that will be M. And I know what the time is for the ith task. 1 minute here, 2 minutes here, 1 minute there. Number of workstations I have in this example, the number of workstations is the same as the number of tasks. It's 3. The cycle time, that's how many minutes per unit I have at each workstation. So that's 2 minutes. That's determined in my example by the longest task time. And finally, what I want to do is find the balance delay, or the percentage idle time. For every unit that comes off the line, what fraction of that time is wasted and not being used to actually work on the product. We saw from my previous discussion that basically 2 out of 6 minutes is wasted. 2 out of 6, that's 33%. Well, is there a nice formula I can use to help me do that calculation? And the answer, of course, is yes. That formula is defined, the balance delay. And all I do is subtract from 1 up here is a sum of all the task times. So that's just going to be 1 plus 2 plus 1. So I got right there. And down here is the number of workstations times the cycle time. Well, the cycle time is 2 minutes, and I've got 3 workstations as well, so that's 3 times 2. So 6 in the denominator. So 1 minus 4 over 6, that is indeed 0.33 or 33%. So the balance delay of 33%, that tells me that 33% of the time that unit spent in the line was wasted. That means that 33% of the time of the workers that were working in that line was wasted if this is a line that has workers and it is not automated. If it's automated, 33% of the machine time is wasted, and so forth. What I want to do is get that percentage as low as possible. Well, before we can do that, we need to be a little more scientific in terms of how we come up with our cycle time. Generally speaking, the cycle time is going to be determined by the target output rate. I mean, the cycle time is the minutes per unit I'm allocating for the parts to be on the line, and that's just the inverse of the speed of the line, which of course is stated in terms of units per minute. So I need a target output rate. Right? If the target output rate is stated in terms of units per day, then I'm going to divide the target output rate into the operating time per day, represented here by OT, where the operating time per day is expressed in terms of minutes, and that's the same unit of time that I'm going to be finding my cycle time in. So this simple formula over here says to find my cycle time, I simply take the operating time per day in terms of minutes per day and divide it by my output rate, which is units per day. So if I want to make 800 units a day and run the line 2 8-hour shifts per day, well, 2 8-hour shifts per day, 2 times 8 hours times 60 minutes per hour is 960 minutes per day. That's my operating time. And my target output, my demand, is 800 units per day. So 960 minutes per day divided by 800 units per day gives me 1.2 minutes per unit as my cycle time. If I want to run 2 8-hour shifts per day and make 800 units a day, that means I got to have a unit coming off the line every 1.2 minutes.